Before starting the power system dynamics part, we'll just go through the elementary concepts of eigenvalues and eigenvectors, and the relation between eigenvalue and eigenvectors and stability. Because most of the topics in this particular course is related to small signal stability, and voltage stability. So eigenvalue analysis and eigenvector analysis are two of the most important techniques which we use to analyze small signal stability and the dynamic performance of the system. So let's start with that, and after going through this, we'll move on to power system stability and dynamics, introduction to power system stability and dynamics. So let's start with a 2x2 matrix to make it more simple. So what's an eigenvalue and what's an eigenvector? We are looking for a vector x and a number lambda that satisfies this equation, the equation 1, which is ax equals lambda x. Or rather we can say that when we multiply by a, that special vector x is the special vector x. That special vector x does not change direction, but just changes the length by the factor lambda. Okay, because lambda is a scalar. So this can be a positive, negative, or 0, or a complex number, lambda. Okay, now if we move everything to the left hand side, then it will become ax minus lambda x equals 0, implies a minus lambda I whole into x equals 0, which is denoted as equation 2. Now, if a minus lambda I is invertible, what does that mean? What is that condition? Can anybody say? What is the condition for a minus lambda I to be invertible? If determinant of a minus lambda I equals 0, then it is non-invertible, right? If determinant of a minus lambda I not equal to 0, then it is invertible, right? This is non-invertible. So if this is equal to 0, if determinant of this is equal to 0, then if this is non-zero, if a minus lambda is non-zero, then the only solution for this equation is x equals 0, which is useless because we are trying to find the vector, right? So this is not a useful result. So we don't want that to happen. So we assume that if the matrix should be singular, then determinant of a minus lambda I equals 0, which is denoted as equation 3. Now, when you find lambda from equation 3 here, when you find lambda from equation 3, we get how much we shift the matrix A, to make its determinant 0, right? 0. Now, what is the amount of shift? It is shifted by a factor lambda times identity. So the matrix A is shifted by a factor which is lambda times identity, so that it becomes 0. Okay. Now the matrix part we'll stop here and we'll move on to differential equation part, and we'll see how differential equations are solved and what is the importance of dynamic analysis with respect to differential equation solution, and what is its relation to eigenvalue and eigenvector. Okay, then we'll connect both and see why it is used. Okay, so here let's consider a differential equation dy by dt equals ay. Okay, and if we have an n by n matrix A, if this is n by n matrix, if this is an n by n matrix, then this is actually n linear differential equations, right? N linear differential equations. Now, how will you find the solution? We have the solution, or rather we look for y of t. Y of t is the solution, which is equal to e raised to lambda t into x. E raised to lambda t into x. Let it be equation 5 and this be equation 4. Okay, this be equation 4. Now, here we can see that all the time dependence is in the exponent, right? Here, all the time dependence is in the exponent. Or rather we can say that the dynamics of this particular variable y, what is the dynamics of variable? Y of t, this is basically y of t, right? It is time dependent. So the dynamics is completely governed by lambda, right? Dynamics is completely governed by lambda. That means lambda is the eigenvalue. Eigenvalue governs the dynamics of this particular system. If lambda is negative, then it's exponentially decaying. If lambda is positive, then it's exponentially rising. Of course, we have already discussed these things. You might have already learned these things in the control system course, but I'm just refreshing these topics so that we can seamlessly enter into the power system stability topic. So this is basically the importance of eigenvalue. Now let's move on to the next part. I have the prepared lecture note with me. I will share it with you, okay, after the lecture. Now if you if you plug 5 in 4, equation 5 in 4, what happens? Equation 5 is y of t equals e raised to lambda t into x, and equation 4 is dy by dt equals ay, right? So basically what we get here is lambda e raised to lambda t into x, right, equals a e raised to lambda t into x, because this is y, right? This is y. This is dy by dt. This is dy by dt, right? This is y. So dy by dt equals ay. This is the equation. Dy by dt equals ay. Now we know that x equal to 0 is not a useful result. So we are trying to find again ax equal to, we are trying to find the lambda, that lambda and x for which this equation is satisfied. Ax equal to lambda x. This is from equation 1. Okay, from equation 1. Now let's see a differential equation. For example, y1 dash equals 5y1 plus y2, then y2 dash equals 3y1 plus 3y2. What's the matrix A here? Can anybody? What's the matrix A? A is 5, 1,
1, 3, 3.
3, 3. Yes, 5, 1, 3, 3. Okay. Now what I need is Ax equals lambda x, right? Ax equals lambda x. Now suppose how many eigenvectors and how many eigenvalues will these equations have, or rather this matrix will have? 2 eigenvalues and 2 eigenvectors. So if x1 equals 1, 1, say x1 equals 1, 1, then if you want to find lambda, then for this particular x1, let it be lambda 1. Okay, this matrix has of course lambda 1 and lambda 2. Two eigenvalues are there. So Ax1 equals lambda 1 x1. This equation becomes this one, right? Now, what is Ax1? What is Ax1? Can anybody evaluate this? Ax1. This 5133 into 11. You will get it as 6, 6.
6, 6.
Okay, 6, 6. And you know that x1 is, what is your x1? 1, 1. So what is your lambda 1? What's your lambda 1? It's a scalar. 6, right? 6 into 1, 1 will give you 6, 6. So this is lambda 1 x1. Okay, so lambda 1 is 6. Now we are going to find lambda 2 because you know that there is one more eigenvalue for this particular matrix. So let x2 be equal to 1 minus 3. Okay, now what about Ax2? Now our equation becomes Ax2 equals lambda 2 x2, right? What is Ax2 in this case? Can anybody evaluate this? Ax2 is 2 minus 6.
2 minus 6.
Yes, 2 minus 6. Now, what is lambda 2? Our x2 is 1 minus 3. It is multiplied with which scalar to get 2 minus 6? Lambda 2 is
2.
2. Lambda 2 is 2. Okay, so you get lambda 2 and lambda 1. We have two eigenvalues and two eigenvectors. Now we are going to find the solution. So you have two solutions basically. Our solution is y1 of t and y1 of t. Y1 of t and y2 of t. Y1 of t, y2 of t. Let this be a vector. Okay. Y1 of t and y2 of t. So we have two solutions. The first solution can be found out by e raised to lambda 1 t into x1 equals, what is lambda 1? 6. E raised to 60 into 1, 1. This is a corresponding eigenvector. Now e raised to lambda 2t into x2 equals, what's the corresponding eigenvector? What is the eigenvalue? Lambda 2? E raised to 2. E raised to 2t into 1 minus 3. Okay, e raised to 2 into 2t into 1 minus 3. Now both are solutions and it's a linear system. Hence, if these two are, if these both of these are solutions, and if it's a linear system, then its linear combination should also be a solution, right? It should satisfy homogeneity. So in that case, if we take c1 e raised to lambda 1 t into x1 plus c2 e raised to lambda 2 t into x2, that should also be a solution. So let us take some arbitrary c1 and c2. We don't know what is the value, but c1 into, what is e raised to lambda 1 t into x1? E raised to 60 into 1, 1 plus c2 into e raised to lambda 2 is 2, 2t into, what is x2? 1 minus 3. Now at t equals 0, this is y of 0, right? Which is the initial condition. So if t equals 0 means e raised to 60 and e raised to 2t becomes 1, then you will be able to evaluate c1 and c2. C1 and C2. So basically we take the initial conditions and find these constants. So what we have done now is we have some dynamic equation in which the dynamics of the variables y1 and y2. Basically y1 is y1 of t and y2 is y2 of t. Rate of change of y1 and y2 with respect to time is y1 dash and y2 dash. This gives the dynamics of this particular equation. Whatever be the variable, it can be rotor angle or it can be voltage or whatever. Okay. So for this dynamics, to analyze the dynamics, what we are going to do is we are solving these equations. If we know the physical equations of this particular system with respect to rate of change of y1 and y2 with respect to time, then we can find the general solution. If it is voltage, then we want to find V of t. If it is rotor angle, then or load angle, then we need to find del of t, right? So similar to that, this can be del 1 dash and del 2 dash, or this can be V1 dash, some bus voltage is V1 dash or V2 dash. So in that case, we want to find V1 of t and V2 of t and del 1 of t or del 2 of t. So that is what we are going to do here. So it is directly depending on the eigenvalue lambda 1 and lambda 2, which governs the dynamics of the system. And the eigenvalue of lambda 1 and lambda 2 is obtained from the matrix, from this equation, matrix derived from this particular equation 5, 1, 3, 3. Okay, so this is actually same as the state equations. What is your state equation? X dot equals ax plus bu. If x has two elements, two state variables are there, then x dot means x1 dot, x2 dot. The vector is x1 dot, x2 dot. Now that is equal to ax plus bu. X is again x1 of t and x2 of t. So you want to analyze the state dynamics. If you want to analyze the state dynamics, you can find the eigenvalue and eigenvector of the state matrix. Here the state matrix is A, right? X dot equal to ax means A is the state matrix. So finding the eigenvalue and eigenvector, you will be able to analyze the stability of the system. Stability in the sense we have already told that if lambda is positive, then it's an exponentially rising signal, and if lambda is negative, then it's an exponentially decaying signal, right? Now, if it is of sine or cosine form, it can be in the form of e raised to lambda t into sine t also, right? E raised to lambda t into sine t. Then if lambda is positive, then it's an exponentially rising sinusoidal signal, right? And if lambda is negative, then it's exponentially decaying sinusoidal signal. Basically, it damps out. In the other case, it amplifies. Okay, so these are the things. Now, let's see some properties of eigenvalues and eigenvectors. Why we are going for eigenvalues and eigenvectors. What about eigenvalue and eigenvector of A squared?